I love this, the moment of silence that captures a room waiting for something interesting to happen. So good evening and welcome to William and Mary's fall lecture, faculty lecture, the Tack lecture. My name is Peggy Agouris, so those of you who do not know me, I have the privilege and honor of being the provost of this great institution. And I can promise you, I'm not going to tell you that you will understand everything tonight, but I promise you it's going to be a fascinating evening. And one evening that, you know, is not going to really make you a lot smarter afterwards, but it will definitely open our minds. And, you know, honestly, I think it will challenge a little bit the way we think. I want to really, again, thank Martha and Carl Tack, whose generosity supports these lectures, which is a great opportunity for us to connect with our community and invite you all to participate in how we enjoy and understand and appreciate the work that our faculty are doing. So tonight is my great pleasure to introduce Dr. Saskia Mordijck. Saskia is Associate Professor of Physics and Class of 1956 Professor of Nuclear Science. For those of you who do not know Saskia, she is the example of how a superstar faculty is. And there's a pun in it, and you'll understand it later. So her research sits at the cutting edge of experimental nuclear fusion, one of the most ambitious scientific pursuits of our time. She earned her PhD from the University of California, San Diego, and has become a leading voice in the global effort to make fusion energy a practical reality. Saskia and her team have attracted significant, prestigious, externally funded support from various sources, like the US Department of Energy, NSF, and others. And among the things that they're working on is the area of making fusion data more accessible, interoperable, and reusable, which is really, you know, work that people characterize as revolutionary. Simply put, Saskia is a thought leader in the great tradition of Belgian problem solvers and thought leaders like Hercule Poirot, Tintin. The only difference is she's real and she's ours. She's part of an international community of scientists who strive to do something truly extraordinary, to build a star on Earth. Yep, that's right, you heard it right. This is really what we're gonna hear tonight. Tonight's lecture is titled, Here Comes the Sun, the Science of Building a Star on Earth. Saskia will take us inside the world of fusion energy and show us how recreating the power of the sun could transform how we produce and use energy and how it might help us confront the climate crisis. Well, I've mentioned it every time, and I know you expect me to. I'm from Greece, and I need to go back to my roots and remember that there was an ancient Greek philosopher, Democritus, who really talked about atoms 2,000 years ago. So here we are today talking about something that really brings atoms together, creating fusion, and really, quite literally, powering the future. Now, those of you who really have been, like me, impressed by a movie of the 80s, Back to the Future, yes, we're gonna be really talking about things that might involve a little bit more than 1.1 gigawatts and to produce power. But I promise you there will be no DeLoreans needed tonight. So fusion holds the promise of a cleaner, safer, and virtually limitless energy source. Saskia's work brings us closer to understanding the plasma behavior, and that would make the promise real. So this evening captures what makes William and Mary truly special. It's our shared pursuit of discovery, creativity, and big ideas that move the world forward. So, without any further ado, I invite to the podium Dr. Saskia Mordijck.
Thank you so much, Provost Arguris. No pressure, naturally, for me now to deliver. So let's see. There we go. The sun, an object in the sky, has been a fascination for humans since prehistory. It shows up in our religion, in our culture, and it should therefore not come as a surprise that scientists always wanted to understand it and study it. And so I had to pick a point in time where I would like to start our story with the sun. And I picked, if this works, 1925. I wanted to start with Cecilia Payne's story. Cecilia Payne was born in the United Kingdom in 1900. As a child, she was absolutely curious. Her father showed her the constellations and the stars. Her teachers were marveled by her tenacity to kind of learn anything, and her dream was to become a scientist. Now, I don't have to explain to you that for a woman in the 1900s, to try and become a scientist was not a natural path to take. So aside from her curiosity, it required kind of a tenacious drive to continue to push forward. And so her dream was to go to Cambridge. Cambridge is where the scientists went. Oxford is where the humanities went. So off she went to Cambridge in 1919. Now, to get there, her father had passed away at the age of 4, meant she needed a scholarship. So not only did she need to pass the entrance exam, she also needed a scholarship to get in. She got both. So in 1919, there she is in Cambridge, trying to become a scientist. Now, a reminder, women scientists at that point were kind of slightly pushed to study botany. That was kind of more a womanly science to study. Math and physics was for men. But for her, so she enrolled in botany, chemistry, and physics because she was passionate by those two other topics as well. And so for her, there was a huge change. Aside from the fact that she had some issues with how botany was done at Cambridge. The people at Cambridge didn't really believe in Darwinism and were trying to prove it wrong. And she was a huge fan of Darwinism, so that wasn't really helpful. The second part was that she actually got inspired. She got inspired by a lecture just like this one, except it was done by Arthur Eddington. Arthur Eddington, in that summer, had traveled to Africa to try and measure the relativity theory from Einstein using an eclipse. And on December 2nd, at Cambridge University, he came back and gave a lecture. And during that lecture, only 4 women were allowed to attend. And Cecilia wasn't even one of them. She got a ticket because one of her classmates got sick. But she attended, and her world broke open. She had always had a passion for the stars, but physics was where she was grounded. So she switched. She went into physics. And so you have to remember also at that time when Cecilia was in Cambridge at the Cavendish Laboratory, it was where all experimental nuclear physics was happening in Europe. This is where the ground base was. She was there with Ernest Rutherford, who kind of led multiple discoveries on that level, and then in the astronomy department, Arthur Eddington. And it is that combination of physics and astronomy that allowed her in 1925 to actually discover that the stars were made out of hydrogen and helium, mostly. Now, how did she get there? Well, other fun story. 1919, when she went to Cambridge, and she didn't choose Oxford, 1919 is when Oxford decided that the women were allowed to have degrees. 1921, Cambridge decided, again, that women were not allowed to have degrees. Now, to be mindful, 1918 is only the first year we allowed women on campus as well. So it wasn't all that strange. And so Cecilia learned in 1921 that she would never get a degree. She would get some papers. And as a result, she also realized that her dream to continue to be a scientist would not work. So there were 2 options. Either find 10 pounds, take the boat to Ireland, and go to Trinity College, which was going to give you the degree if you'd done the classwork, or get a scholarship and come to the United States. And so she decided to come to the United States. She went to Harvard, which, by the way, didn't give her her degree because Harvard didn't give degrees to women in 1925. It was Radcliffe. But she came to the United States on a scholarship to pursue her passion in astronomy and get a PhD. So the question is, how do we know what a star is made out of? It's not like even at that time I could fly a rocket there. But even now, it's not like I can fly to the sun and actually get a rocket, get some samples, bring it back to the lab, put it under a microscope, maybe kind of twiddle a little bit with it. You can do that. So to do that, we actually needed to do some of the science we had learned right at that time. And for this, we're going to have a little demo, and I'm going to ask Shannon, who works at Princeton Plasma Physics Laboratory, to come and help me.
Hi.
Hi, Shannon. How are you?
Good. How are you?
Let's take this foil out.
All right.
So for you all, you should have special glasses. Yes? These are your magical glasses, and so you should put them on. And we are going to show you a little bit of how scientists used things like your glasses to actually learn something about the stars. So Shannon, walk us through this.
So when you turn a gas into a plasma, it gets super hot and it gets excited. And so it starts emitting light. And it's what the sun and the stars are doing. The sun and the stars are plasma. So let's show you a plasma that you definitely have seen before, perhaps in a shop window. Does that look familiar?
Yeah. Anybody recognize this? If you're old enough, you recognize this. Yes? Maybe the younger crowd doesn't recognize this anymore. What is this?
Woohoo!
Woohoo!
And if you see a neon light that's not this color, it's not neon. It's a different gas.
Yes. So.
But check this out. So this is a diffraction grating that works just like a prism.
So you can see it too with your glasses, but this is the way, if you cannot see it with your glasses because you're too far away, look up at the screen at the top.
And you can see these are spectral lines. These are the lines that are emitted from each particular gas has its own signature pattern of lines, its own favorite rainbow. Happy Pride. So every single gas has a signature pattern of light at different wavelengths. And so what colors do you see here for neon? Green, Yellow, some red and orange. Yep. Excellent. All right, so we're going to try a different gas.
Very different in color. Look at those.
What colors do you see?
Blue and green.
All right.
Good job.
Does anybody know what gas this is?
No.
No? I'll give you a hint. Neurotoxin. Mercury. Yes!
Where are the chemists when you need them?
All right.
Okay, let me hold. There we go.
So, anybody know what this one is? Oh, I heard it. Yeah. So this is what we start with in fusion, actually.
Yeah.
And then,
Last but not least.
and this is what we wind up with fusion.
Yes. So these last two were the ones that were observed plentiful. Yes. Okay. However, there we go. So about 100 years before Cecilia did her thesis, Fraunhofer kind of discovered 570 lines. So when he looked with this kind of technique at the sun, he was able to find 570 lines. At that point, they had no idea why those lines existed, yes? A lot of times we discover a lot of things in science we can't explain. And it took a little bit longer until Kirchhoff and Bunsen kind of then discovered that each gas would emit very specific colors. And in fact, one of the things that happened is there are some lines that they found they couldn't match to any gases. And somebody said, well, that must be very specific to the sun. And going back to the Greek roots of one of our people in this room, instead of calling it helios, which is, I think, the Greek word for sun, called it helium. Now, Cecilia didn't have a nice spectrum like we do. This is what she was working with. Now, the other thing that happens is, if you have more gas, it burns brighter. But if you put it at a higher temperature, it burns brighter as well. And so what she did is she actually did hardcore calculations, taking into account the temperatures to be able to distinguish how much was there of each. And to give you an idea of how groundbreaking that discovery was, this was one of the things she had to put in her thesis. And I want to point you to the last little bit, which says, is almost certainly not real. She was forced to put that in. At that point, Henry Russell, who was the director of the Princeton Observatory, was part of her committee. And he needed to sign off. And he was a firm believer that the sun and the earth were made out of the same stuff. Mind you, it gets better. In 1929, he published a paper with like a tiny mark to give Cecilia some credit, claiming exactly this. He used a different technique, and he got a lot of credit for this for multiple years. And it is much, much later that she got credit for all the original work she did. And actually, her PhD reads actually really well. She's an excellent writer. It's actually kind of really, really nice. And so this is now kind of considered one of the best PhDs in astronomy. It was also the first PhD in astronomy at Harvard. Not technically Harvard, Radcliffe. But it was kind of the start of that thing. So the challenge is, the sun is made of hydrogen and helium. There's no chemical reaction that can explain this. Yes? At the same time, people had discovered radioactivity with Marie Curie much earlier, and they understood that something was happening that they could not explain at a chemical level. At the other hand, you have some theorists running around like Albert Einstein, and so if there's only one formula that anybody knows in physics, it's this one, because it's on every single t-shirt. Yes? I also promise you, it's the only equation that will show up in this talk. So what happens? What does this mean? And so it's only in 1932 and 1933, so after we've gotten there, that people discovered the neutron and were able to prove this theory correct, and were able within 0.5% to show that this equation was correct. And it is this kind of work that then allowed us to understand that what radioactivity really was a very large atom falling apart into smaller pieces. Now, this is fairly easy to do. Anybody who's played with a baseball in the house knows this, yes? Breaking stuff is really easy, yes? Just throw it hard enough, eventually it will break. Fusion, which is the opposite side of this thing. So what happens on the fusion side? On the fusion side, what you need to do is you need to somehow take two very small things and put them together. And so for this, if you are sitting with somebody next to you, you all should have a magnet. And I want you to work as a team. So when you pull out your magnets, one of the things you should find is if you have your magnets, they should be in different colors. And by the way, it doesn't matter. One of the things you do is when you have your magnet, try and bring it together. Does it work? No. They're good magnets. You can use them for your fridge if you need to kind of hang something up. So these are magnets. They have a repellent force. And what is happening in the core of these atoms is the same thing. They are positively charged. So it's not a magnetic force. It's an electrostatic force. But what happens if you want to push it together, they will repel. So what happens is if I try and bring two things together and I do this at a very slow speed, they just will serve and kind of not touch. Okay, try again. I can make this go faster. Yeah? So when we say go faster, that also means we say increase the temperature. For a physicist, when we make particles go faster, we make something hotter. So it also means that eventually if I make this hot enough, these two particles can come close enough, and at that point there is an attractive force that actually pulls them together. At this point I want to stop and just mention, because I know I will get a question on this, this is why cold fusion does not work. Okay, we're not talking about cold fusion. You need hot temperatures to make fusion work. So we are just not going to be talking about cold fusion. Just not doing that. Okay, now, so we have all these pieces and particles at that point, and still we had to wait until 1938 before somebody actually figured out the whole chain of how we went from a hydrogen atom to a helium atom, because it's not a one-step process. So this was done by Hans Bethe. And it kind of shows you again the importance of just showing up sometimes when you have to. He was invited by Teller to go to a conference. And he said, like, no, this is about stellar stuff. stellar atmospheres. Not my thing, don't want to go. And he was still convinced to go. There were only 34 people invited to the conference and the workshop. And at the end of the week, he came up with this. He did follow it up with a second paper, and it got him a Nobel Prize. Just shows you sometimes showing up is just as important, yes? Anyway, but this paper was instrumental. So this paper influenced local history when it came to fusion. Because in 1938, Arthur Kantrovich, who had a master's degree from Columbia, had started working at NACA Langley, which is now NASA. And so he was working there on wind tunnels. That is what they did, you know. But he got inspired by this paper, and he said, I want to do fusion, and I want to build a fusion reactor. So what do? You convince your boss, you embezzle $100K in money that you shouldn't be using for this thing, and you build a clandestine project. Okay, and so what did he do? And he was pretty smart. So he was like, these are going to be hot particles, and that means we are going to use a magnetic field. And so Shannon and I will show you a little bit of how a magnetic field can actually influence a plasma. So you can use your spectral glasses if you want, but you don't have to. So.
Yeah, first I'd like you to identify.
Yeah, you'll be back on, I think, soon.
The first I want to ask you if you can identify this gas based on the rainbows that we saw before.
Anybody recognize the rainbows? Neon? Yeah. No, not neon. Not enough orange.
This was neon. Yeah.
It's mercury. Okay.
So this is mercury. This is just a regular fluorescent light bulb like you might have in a doctor's office or a grocery store. But only half of it is coated with this phosphorescent paint that kind of sucks up the light waves that are coming off of the plasma and re-emits them as something closer to natural light. So if you can see with the glasses, and you can also see with this.
I will hold it.
That's okay, I got it.
You got it?
Yeah. So you can see on the bottom half, it's closer to a full spectrum, closer to a whole rainbow, and the top half is just that blue and green. But what's interesting about this is the interaction between charged particles and magnetic fields. So can anybody see what is in these little, what's right here?
There are two
What are
magnets.
these?
I can see it, but I don't think they can. But there are two magnets. So
But
these
we've
are
got
like the
some magnets
magnets
on
you
it.
have too.
So let's see what happens when we move these magnets. Can you see that? So we're actually squishing the plasma. We're telling the plasma to go, where to go using the magnets. You can't do this with regular gas. You can't like wave a refrigerator magnet through the air and tell the gas where to go. It has to be charged particles. It can only do this one. So what's one of the three properties of plasma? So plasmas glow, they give off light, they conduct electricity, and you can move them with magnets.
Yes. Okay. Thank you, Shannon.
Of course.
Okay, so with that, how does this work? So this was called the diffusion inhibitor, so nobody would kind of go like, whoa, they're doing fusion. It was a very, very clandestine name. Anyway, so what they, oops, wow, now it went really fast. Okay, one more. One more. There we go. Okay, let's do this. Okay. If you have a charged particle somewhere in this room, and there is a charged particle somewhere in this room, I guarantee you that, this is what it's doing. Yes? It is moving randomly throughout the room. Now, if you have your magnet, if you find the one random particle in the room, this is what your particle is going to be doing. It is going to have a very, very, very tiny oscillation around this one magnetic field line. So the idea behind a diffusion inhibitor is like, well, let's take this magnetic field line and let's make it go around. Because if it kind of goes around, then this particle will eventually start moving. It will kind of rotate around it very tiny. I just couldn't do it to scale. Also not a fine hand. And so this is what happens. So it should stick on that magnetic field line, yes? And so the way to build something like that is you take one of the donuts outside, or something similar, and then you wrap it with a copper coil. You add some water cooling to it because the copper coil will get hot. And so you'll get a magnetic field like that. So these are then the copper coils. And that's what they did. Now, the second thing they did is they then needed to heat the plasma up a little bit because just a magnetic field doesn't create a plasma. So in order to kind of heat it up, the same as we do with our little tubes, you can actually heat it up with a microwave. Now, to give you an idea, their microwave was about 150 watts, which is about 10 times less than your microwave at home. And as you imagine, they didn't really measure much useful neutrons, X-rays coming out of this thing. I have no idea how big this thing was. It's a clandestine project. There is no drawings of it. There is no pictures of it. But they at least tried, yes? 1938 in NASA Langley. We forget how important Virginia was for fusion. Okay. And anyway, the thing that stood out to me was, to him, this was a heartbreaking experience. And I completely relate. I chose fusion. I had to just build a whole future around this. I wanted to make this a career. He didn't make it a career, but he went back to graduate school and he did a ton of really amazing work. Okay, so the damn thing didn't work. We fought a Second World War. And then finally, eventually in the 50s, we had time again to do science. And so people were curious about fusion. I mean, we kind of had gotten the fission part down, so maybe the fusion side would be just as easy and quick to go. And so especially in the USSR, the United Kingdom, the United States, Argentina as well, different, again, not a good story, people started to work on fusion. They were coming up with multiple ideas to try and do this, and magnetic fields were one of the ways to go. So to understand better how far away people were from doing fusion, let's first understand what we need to actually achieve fusion. So the first thing we need to do is, naturally, I mentioned, we need to find a criterion. There are going to be times where whatever I'm doing to this plasma inside this thing, it's not going to fuse. We've had multiple plasmas up here, and I guarantee you not a single one was fusing. Okay? So we didn't generate any fusion in these plasmas. So that means we need to figure out a criterion where we know that the moment that we put some energy in, that there is more fusion energy coming out of that plasma than we actually put in as humans. And so that's a really important criterion. To do that, the first thing you need is really high temperatures. Yeah, that's challenging. Now, I was going to make a joke if I saw the chair of the philosophy department here about how our kids are really good at this because we caught them once in the backyard, both of us together, kind of doing this, and they were actually successful. So anyway, to give you an idea of scale, the sun is actually only 15 million degrees. We need something that is 10 times hotter than the sun. Can you imagine the challenge? That's a huge step. Now, as you can tell, that's not enough. I mean, then I'm somewhere on this curve. I need to go up somewhere on the y-axis. So the second thing you need is fuel. You need something to fuse, yes? So you need enough of that material to fuse. And so in this case, I can put a lot of gas into this thing, but the gas is not the part that is going to be fusing. I need to make sure it's ionized. So my fuel needs to be ionized. So I need a lot of fuel to do this. It's really tiny, but still a lot in some sense. The other part we need is, okay, if you got all this together, see, I knew. If you get all of this together, I still need to trap it in one place. Yeah, I can do this, maybe, I can make this happen in an accelerator. You can do this. You can shoot one particle at another particle. You can get them to fuse. But the problem is that is kind of one, it requires a lot of energy. Once the particle has fused, there's not a second particle around to do it, so the fuel is gone. And third, I didn't really trap them very long for there. I just did it once. So we need to come up with a different way of doing this. And so in the 50s, a lot of people and a lot of labs were trying to do this. And it was kind of just a whole lot of things going on. The other part that is going on is there are multiple ways of doing fusion. And the one that we are going to do here on Earth is not the same one that is happening in the sun. So that was also one of the problems with the fusion inhibitor, is they chose hydrogen. They didn't have anything else at that time. Hydrogen requires much more energy to get to fusion than the reaction we're choosing. So deuterium and tritium are hydrogens, just a little heavier. Deuterium has 1 extra neutron, and tritium has 2 extra neutrons. When you then combine these two, you can get helium, which is really great byproduct because we're running out of it for hot air balloons, and neutrons. Okay? So that's the thing. The idea then is that, the idea there is, I'm not lying in pointer. The idea there is that then we would take the thermal energy that's in the helium and we would put that back in the reaction to keep it going. So that's a sustainment, yes? If I don't have to heat it, my fire keeps on going. And then the second one is I have this neutron, and somehow I'm going to do something useful with that down the line. That's kind of the idea. At least physicists, we kind of go like, once we got the fusion going, the neutron will take care of itself. Okay, and then in 1958, this is what the British press was saying. The British press was completely excited because they had gone to Culham. It's actually, I think this one was in Abingdon, just south of Culham. And so the British had built a machine, and they claimed that they are getting fusion neutrons. And so naturally, everybody was all over the place, a son of our own. So I think what we want to do now is we want to talk a little bit about what that machine does. Why was it built that way? So the one thing I want you to notice about this machine is that you have, like, again, this circular donut thing, but you have like this huge thing, that kind of arm that is reaching into it. And so that arm is actually what we're going to be talking about, because this was the idea they had. Oh, I hate my pointer. Okay, we'll have to go back. We're going to do the inductor. No, this is up. There we go, inductor. Sorry about that. So we're going to talk about what an inductor does, at least Shannon is. So you want to?
Yeah. So we're going to talk about one of the ways that we heat our plasma in a tokamak, a particular kind of fusion reactor. So first I want to show you these. So what do these look like? Copper rings, yep. All right. And what does this look like? I heard somebody say what it's actually called, yes. But it's, just it's a copper wire wound around a pole. And it is purple only because it's got plastic insulator around it. And so what do you think is going to happen when I turn this on? Shout it out loud and proud.
It's going to jump.
It's going to jump? Okay.
I'd like to explode.
So many little kids say that. I do these presentations for like...
I'm a little kid, just in a metal body.
Why would I put something on the stage that's going to explode? I will not do that.
Oh, I don't know.
All right. So how many people say it's going to jump? Okay. How many? Does anybody have another idea of what it might do? Spin. Okay. Raise your hand if you think it's going to spin. Okay. Don't be too attached to your hypothesis. It's cool to be wrong because you learned something.
Yes.
All right.
It does nothing.
Yeah. Who says it's going to do nothing? Raise your hand. All right.
There we go.
Thanks, Tony.
I like pessimists.
All right. Let's see what happens.
What?
All right. It went up. And now it's kind of floating. Why?
Yeah.
All right. Woo. Actually, let me do it a little bit longer.
So what is happening while she does that and has fun?
It's so much fun.
It's so much fun. Woo. Okay.
Well, I'm going to have some people test it, though, for me.
Yeah. Okay. So one of the things is the Zeta machine used this. So what it has this huge inductor through the center of this thing, of this torus. And then it is flowing, what it does is you have like a ring of current flowing around. And the idea was that that current would pinch the plasma together. However, they were not as hot as they should be. They didn't reach the temperatures they needed to be at. And this was actually the US, they kind of mentioned and said, we don't believe you. Yes, you have a bunch of neutrons, but we don't think it's a high temperature. So challenge here was that, okay, and then the US replicated the experiment, not just the calculations, and they did find that the temperatures were much lower, and so they had to kind of bring back the claim. By the way, this is not going to be the first and the last time that fusion claims to have solved all problems. Fair warning. So the thing is just that it didn't really work, but it was still an instrumental kind of move forward because in 1958, fusion got declassified. And actually, fusion was one of the leading sciences to bring the East and the West together. I mean, Shannon joked to me there's only 2 things where we collaborated on. It was ballet and fusion. I didn't know about the ballet, so I learned something new today. Anyway, so in 1969, at a conference where East and West were meeting, it's actually 68, the Russians showed up and said they had reached 1 million degrees in temperature. And so the West was naturally skeptic. We'd all been kind of working on this. And so they had built a tokamak. Okay. So in some sense, what they had done is they'd taken 2 things together. Remember the diffusion inhibitor? We have like this magnetic field that goes around in a circle, but the plasma leaks out pretty fast. Actually, if the people would have taken E&M in grad school, they would have been able to calculate that before they built it. The thing is, what the Russians then did is they then combined this with the aspect that was in the zeta, in this pinch. They added an extra current to it. And actually, when you combine both, you get something really stable. So they built this tokamak. Now, the thing was, they didn't know how to measure the temperature directly. They were making inductions based on other measurements going forward. But luckily, you know, after the Zeta machine failed, people didn't just shut down the machine and walked away. They wanted to understand why. And so in order to understand why, they built multiple diagnostics. And so one of the things they built, oh, I'm doing Van de Graaff first. Personally, I'm doing Van de Graaff first. Okay, question is, how can you actually get a current to run in a vacuum? And for this, we'll actually need a volunteer. And so actually, I need a volunteer, and there are some limitations on how much hair you have and stuff like that. So as a result, I'm asking our provost to actually join us today on stage to actually be our little guinea pig for this.
While she's walking up here, I'd like to note that when I pass these around to the audience, some of these were hot, and one of them was not. And the one that was not had a break in it. So there was electricity going through these, and that came from the electricity going through here, and it generated a magnetic field. That changing magnetic field induced a current in these rings. But this break prevented the electricity from going through. There's a little gap in there, and so the electricity did not cross that gap.
So, and that's the challenge, because in a tokamak, there is no metal there to drive your current. So how are we able to do that if we don't actually have any metal there? So for that, you're going to be our demonstrator guinea pig.
All right. You sure you want to do this? All right. So first I'm going to turn this on.
So what is that actually, Shannon?
This is a Van de Graaff generator. Is that a little scary? Yeah.
You can see it sparking, huh?
What does it look like? It looks like lightning. And what's that sound? It's little baby thunder. All right. So in this case, it is a high enough voltage to bridge that gap, to turn the air around us, which is very high density, into a plasma. So you're seeing the plasma. You're not seeing the electricity. You ready? All right. Go ahead and stand on the stool carefully. Okay. All right. You're going to follow my instructions exactly, okay? All right. Do you think you're going to get shocked?
I'm assuming based on the sound.
Well, let's see. All right. I want you to put your hand flat on the ball and don't take it off. Just one hand flat on the ball, on the big silver ball. Did you get shocked?
No.
Why?
I don't know, because you have that thing there.
All right.
Yeah.
Okay. Do you think you'll get shocked when I take it off?
Yeah.
Let's find out.
No.
No? You didn't get shocked, right?
No.
Do you feel a little tingly?
I feel it here.
Yes. Yes.
All right.
If
So
you-
what I want you to do, leave that hand on that ball. If you accidentally take your hand off the ball, I want you to just put your hands to your side and step off the stool quickly and move away. All right? Don't touch the ball again after you let go. Oh, what's happening? All right. Take that free hand, leave that hand on that ball, and take that free hand and kind of lift your hair a little bit. There we go. Can you see it in your reflection in the ball?
You can look yourself, you can, or on the screen.
This is the best hairstyle. This is great. This is what, yeah. Lots of volume. Lots of volume. I love it. Oh, it's getting really good.
This is not going to be shown anywhere.
Here, stay real still. All right. Now, I think you're going to get shocked, okay? I know you said you didn't want to get shocked, but I think you're brave. I believe in you. We need another volunteer. Tony, would you?
Tony.
All right, when I do this for school groups, I ask if they don't want to get shocked. If they say no, that means no. Nobody touch her. All right, no means no. But in this case, you're willing to get shocked, right? This is with your consent, right? All right, it looks good. All right. Now, what I want you to do is sort of like Sistine Chapel style, stand to the side and, wait, don't get too close.
Far enough.
All right, I think she's built up enough charge. I want you to touch fingers, and everybody watch closely between their fingers.
Yeah.
Oh, yeah. Did you get a shock too? Yes. Awesome. Okay. So want to do it again? No. Well done. All right, and I want you to just, when I count to 3, take your hand off the ball, put your hands by your side, and step off the stool quickly.
Yeah.
1,
let's give her some
2,
space.
3. Off. Woohoo! Well done.
I'm so sorry. Thank you. The benefit of being invited to give a talk, you can do this to your provost. Anyway, so you have to imagine 1969, we're at the height of the Cold War. The Russians need to prove that the temperature in their tokamak is actually really as hot as it is. And so they reach out to their British colleagues. The British colleagues at that point had built something called a Thomson scattering system. It's a laser-based system that allows you to measure the temperature inside a plasma. Now, how do you get that Thomson scattering system from the UK to Russia? Well, there was only one plane once a week by one airline that could take all the equipment, which was Pakistan Airlines. And they actually flew an extra flight for them to get there. And there's 5 British scientists that actually moved to Russia. And they were working at the top nuclear institute in Russia. This is where the Russians were developing nuclear bombs, yes, and nuclear technology. And they were invited there and given freedom of the lab to do what they needed to do. The challenge was when they got there, naturally, is nothing works the way it's supposed to work, because on top of that, the temperatures and the type of plasmas they were going to measure was very different from the Zeta plasma. So at first, they didn't get enough of a signal, so they had to bump up their lasers and get a bigger signal. Naturally, the moment you get a bigger signal, every single mirror and lens breaks. So something that should have taken 2 or 3 months took actually 6 months, and a ton of diplomatic pouches from the UK to Russia to bring the equipment over fast to get things done. But they were able to confirm this measurement. And this completely changed the world of fusion. In fact, even the day that they were submitting the paper to, I think it was Nature, about these results, they also phoned the United States. And they said the results are true. And the United States at that point had taken a different path, and they said, we're done. They changed their design, they built a tokamak, and 4 months later, they were up and running as well. And so this set the tokamak race in motion. And so this has been the machines that I've mostly done all my research on. I've mostly worked on tokamaks, and I've taken some of them are the ones that I actually have worked on. So the thing is just they're all toruses. There's always like this center in there to have the inductor. You can see a lot of holes and things on the sides, because while the tokamak made a lot of progress, it did not get into that blue box where we would have more fusion out than fusion in. And so as a result, we kind of needed to understand what was happening. So all these holes are kind of places where we can put measurements, techniques, because those improved vastly from when we had one Thomson data point. They're also places where we can actually heat the plasma further. And so one of the things that I want to show you a little bit is a little video of, and this is a big device that they're building in France. And so this is the machine they're building up in France. It's called ITER. Oh, sorry. There we go. Let's play this. play. Yeah, okay. Okay, so what's happening when you actually build a tokamak and when you want to power it up? The first thing you do is you turn on these big coils on the side that create this toroidal magnetic field that is in there. The second thing you do is you fill it with some gas, a little bit. It's normally a vacuum, and then you turn on that solenoid. And then what happens is exactly what you saw happening with Peggy. It gets ionized, yes? And so the current starts to run. The second thing that happens is for the people that were able to touch the coils is this will have resistance. So it's also going to heat the plasma up. And so this then kind of creates more plasma, more plasma, more plasma. Eventually, it reaches a temperature where everything is a plasma. And at that point, you cannot use the current anymore to continue to heat it. At that point, it's not even hot enough. So what we have to do is we have to come up with different ways of heating the plasma. And so one of these is like an accelerator. You actually accelerate particles to really high speeds, and you shoot them into the plasma, and then through collisions, they will deposit their energy in the center of the plasma. Another way is, again, to use your microwave. Yes? Microwave at very different frequencies than what you need. But you can use antennas, and these antennas can put waves in, and a little bit like a surfer surfing a wave in the ocean, these waves will kind of give those particles energy and make the whole thing go forward. So that is one of the ways that we kind of are able to heat these tokamaks up to higher temperatures and kind of make things go. There we go. Now, in the 50s, the US had been on a different path. They built a little stellarator. And the concept was similar to a tokamak in the sense of that they understood that just one toroidal field wasn't enough and you needed to kind of have like twisted fields. Now, the challenge with a stellarator is that once you build it, the twist of your fields is kind of set. And so while this is not a bad idea, the challenge is that it wasn't functioning the way it was supposed to function. So it wasn't reaching the conditions it needed. And it actually took us until the 90s and the 2000s where we actually had the supercomputers to be able to predict what these plasmas would look like and to then design stellarators to compete. And you can see the one blue dot in this thing right now. There will be more of them later. This one blue dot is now starting to compete with the tokamaks, something that didn't happen at first. And so this gives you a little bit of an idea of what a stellarator looks like. So a stellarator is, again, a toroidal device. It is going to be using magnets. But in order to create the twist that you need, that the tokamak has, you need very funky shaped coils. And building those with very high precision tolerances is a mess. The benefit of the stellarator, if you're able to do it, is that it can run continuously. Because counter to this inductor, I don't have to pulse it. So once I turn it on and I have my plasma going, I can go home, I can have lunch, I can have dinner, I can come back and I can check whether the whole thing is going. A tokamak, I can't do that. I actually have to be there and start it up every single time again and again. So this is the stellarator. And so this is actually a US invention, and it is now being really pushed forward. And there's a lot of companies and a lot of people that are looking at kind of maybe this as a step forward for fusion. Okay. So even though the tokamaks were winning the race to fusion, they didn't win it. They never really reached the blue part. We came close. In 2021, the JET tokamak, the largest one, actually did achieve some records, and it kind of repeated them and broke them even further. It was in 2024, there was 69 megajoules. And I know for a lot of the audience, they kind of go like 69 what? 69 Mars bars. Or Snicker bars, if you prefer Snickers. But for less than 1 gram of tritium. So that's, that's very little food for a lot of energy. The one that won the race is actually using lasers. So this is a very different concept. And I actually would like for you to now maybe take out your stress ball. I think we're kind of getting a little bit more stressed. There's more physics in this thing. So let's kind of take out our stress balls. So, with the magnetic field, we try to more squeeze it uniformly. Now with the lasers, one of the things you have to imagine is if I'm going to have like a little ball and then I'm going to be shooting a bunch of lasers at it, it's like as if you take all your fingertips and try and squeeze this thing uniformly. Like, try and squeeze it as uniformly as you can. Does that work? No. There's always bubbles out on every single thing. And so this was one of the big challenges with the lasers, yes? They constantly were bumping into instabilities, is what we call it. Things weren't working. And so NIF was actually built about 10 years ago with the promise of reaching ignition immediately. And it didn't work. It took until 2022. And so this was a big announcement. And this is the first ever ignition anywhere on planet Earth. I can't speak for aliens out in space, but on planet Earth, first ignition ever. And so this was a big deal. And to give you an idea of how big a deal that is, in December 2022, this was announced. Our main conference is in October, November, and they couldn't say anything at that conference. The paper had been submitted, the things had been done. Then you have other people. I was involved at that conference with organizing events for women in plasma physics, and so I have a group of women helping me out do this, and we're meeting up in August, and so those work on the ignition side of things. They go like, yeah, we can't say anything, but we did it. Can't say you anything. And then the next thing is like, now they want to do it again. And I wanted my own plasma shot. I didn't want to do ignition. Anyway, so what do the lasers do? So this is a, it's crazy. I mean, honestly, you know, it's ridiculous the amount of precision that comes with it. So in order to do this correctly, you need to start from one single laser pulse. One single pulse gets started and then gets sent out to make 192 laser pulses. Now, this one tiny laser pulse is a tiny laser with very little energy. So one of the challenges is that you need to add more energy to each of these laser pulses. So the whole site is about the size of 3 football fields. And this is really slowed down by 1,000,000 times. And I actually I probably won't do the whole video because I don't have enough to kind of keep repeating how often it's going back and forth. But what is happening is it's being given more energy at every single pass, but then at each of those passes, it also needs to be refocused, it needs to be reshaped, and it needs to be precise. Because at the end of this thing, all these lasers need to come together in one large cavity. And so this large cavity is here. It gives you an idea. This, and we have 2 humans in it for scale, always, gives you an idea. So this is this large cavity. Each of these holes you see is where one of the lasers is coming in, yes? The second thing you see is like this strange pencil sticking out. This is not somebody kind of photobombing a picture, okay? This is literally, this very, very large arm is there, and it is as large as you can imagine with the 2 humans in it. At the outermost tip of that point, they're going to put this little golden capsule where, again, it is to scale to the eye of the person in front of it. And they need to position it perfectly with how the lasers are coming in. So the challenge is, even though they made ignition, they can do only one of those every 12 to 24 hours because of the amount of time it takes to line everything up and to be as precise. But they did win the race. Okay? So this gives you a little bit of an idea of the race to fusion in time. So the thing is, what you can typically see is that we started out in the 60s, 70s. What was really instrumental for fusion was that in the 70s, oil was expensive. That was really useful for us because then people wanted to fund alternative research in energy systems. But you can see that we kind of are at this cusp now where multiple things could be reaching ignition. NIF was first, but we are in the middle of a bunch of devices that could do this. Okay, we're done. We got fusion. It works. From a physicist perspective, we might be done at this point. But, you know, you still don't have any fusion energy coming out of your power outlets, do you? No, you don't. So the thing is, we still are stuck with this one neutron that is coming out. What I said, we would kind of do something useful with it, yes? So while the fusion is working, we now need to somehow get to producing electricity. And so what we need to do is we need to capture that neutron. So that neutron is really 14 MeV. To give you an idea, that is much faster than any kind of neutrons we typically generate in any other type of reaction. So what we will do is we need to kind of somehow find material, and we are going to be using mostly lithium. And what will happen is when that neutron kind of comes in there, there will be so many particles in there that eventually it will bounce against one, it will give off some energy, it will change direction, it bounce against another, and so at each bounce, it will lose energy. And that means the particles in the system will heat up. And so when they heat up, you want to cool the whole system. And this is then where we go like, okay, this is where the engineers can take over. We're going to just use water, and we're going to the water is going to heat up. We're going to gets to steam. We'll put the steam through a turbine. The turbine will start turning. Cold water comes out. I make sure I have a generator attached to this whole thing, and magically we'll have electricity. The reason we don't really worry about this part is this is how actually your coal power plants are powered, your gas power plants are powered, your nuclear power plants are powered. So this last part, we know how this works, and we know how to do it. So we at this point, we're good. The challenge is that, nobody's ever built a fusion reactor. So the question is still like, how do I take this, make sure I capture all these neutrons somehow, and then still get electricity out? And so this is one example of a company who's trying to build a fusion device, actually in Chesterfield, Virginia, not too far away from us. And so they're going to be using this idea, and they're going to be using some lithium blankets to do this. Okay. So with that, we are at the question, well, why doesn't it work yet? We seem to have a plan. Why doesn't it work yet? Well, because you would like to make sure that your oven works every single day. I would like to not have my simulations stop because somebody on campus broke another cable somewhere. So why is it not there yet? When we as humans want electricity, we don't want it 99 out of 100 days. Yeah? You don't want a random day somewhere in the middle of the year to run without electricity. And so what we need to do is we need to run plasmas and fusion devices that are guaranteed to be stable. So this is an example of an instability. This is not going to cause any major scale problems. Yes, this is not going to lead to some kind of disaster. But these instabilities, if they're large enough, could make the power plant stop. And as a result, you would run out of electricity. There would not be a catastrophe, but it would be an issue we would have to deal with. And actually, this is my favorite instability. This is an edge instability. And it's one we actually have been studying in my lab, and actually started studying it when I did my PhD. And so we actually know how to manage this. So we've learned a lot, and I cannot take credit for being the first to know how to manage it. I came in once they knew how to do it, and I was figuring out more physics. But we know how to manage an instability like that. And we know how to manage other instabilities. So that is one where we've made a lot of good progress in the last few years. But we need to make sure that we have 99.9% reliability. The other aspect is that if you have something that is 10 times hotter than the sun, at some point it's going to be touching a wall. One of the things we've been doing in our devices is we make sure that we target specific walls so we can protect them. And we know exactly where all the heat is going. And so this was an example of a plasma. And this is actually the 69 megajoules record-breaking shot on the jet machine, where they were running a plasma. And you can see at the bottom, you can see the pink light. That is where the plasma is touching the wall. And so the other thing we do is to test at which point materials will melt, is we do explicit experiments. So what you can see here is a collection of materials that have been undergoing some kind of destruction on purpose by scientists. I want to be very clear about that. We do these things on purpose so we can test what the limitations are, and that we can test how to build a safe system if we need to actually deliver you with electricity. Complete open questions we have are neutron damage. Since we don't have fusion devices, we have no idea how the neutron damage to any of the materials will actually affect our performance. And this becomes really critical because, we want our neutron to leave the plasma, get out of the first wall, and then eventually come into this lithium barrier. But to do there, it will pass a few things. And so one of the things is it can displace atoms. And these atoms, then you have holes in your material, and other materials can creep in. And the one we're most worried about creeping in is tritium. Because while tritium is a fuel, it is also radioactive. And so if that gets stuck in the wall and we are not able to get it out, you are stuck with a wall that is radioactive. Not for millions of years, but still radioactive, something you need to worry about and take care of. And so to better understand that, this is something that we are not actively doing, but people around the world are actually building devices. And actually one of the devices is actually just down the street. So this is JLab. At JLab, they shoot particles at each other. And as a result, they actually create a lot of neutrons they don't care about. And so we're thinking of maybe we could take those neutrons they don't care about, they put them in a beam dump, and maybe we can actually use that beam dump to start studying materials for fusion. The other one we have, oops, what happened now? Oh, I went all the way wrong. Damn it, wrong button. I closed my thing. The other one we're building, okay, there we go. The other one we're building is MPEX. So this is a device at Oak Ridge, which again would allow us to test the materials under conditions that fusion reactors would be kind of withstanding. So we are still doing quite a lot of research to get there. Last but not least, tritium. So tritium, the US made quite a lot of tritium between 1955 and 1996, about 225 kilograms. Anybody want to venture why? Thank you. However, because tritium actually has a very short half-life, it means that every 2.5 years, about-ish, half of your tritium is gone. It doesn't exist anymore. It is not like disappeared in the environment, it's just gone. It doesn't exist as tritium anymore. So that means that even though we created 225 kilograms, in 1996, only 75 kilograms were gone, were left over. Now, anybody who has a calculator and knows how to calculate half-life can do what I did, which is like, how much is left in 2025? 14.7. So what if we have to wait another 12.5 years for fusion? 7 kilograms left? Another? Another? At some point, we will not have the amount of fuel we need to actually even get this whole thing started. So there is an urgency behind getting this done, and there's an urgency in finding other ways than tritium to do this. And there are some people that want to use other methods to do this. The challenge there is that these methods tend to require much more energy, so they're much more challenging. Now, this also brings in a problem, and so the other question is, like, even if I have all the tritium in the world, how the heck am I going to fuel something that is hotter than the sun? I mean, I don't see this comet coming back. I don't think it even makes it to the core. So how am I doing that? And if you want to know that answer, you have to ask my students later today, because that is the research we are doing at William & Mary. We are trying to figure out how to fuel a sun on Earth. Okay, so I know I'm going to get this question. So I want to kind of get there. When can we expect fusion to work? Huh? Never. It's always 50 years away. Or, you know, if I read the news, apparently it happened in my backyard yesterday. It's never black and white, is it? It's not going to be never, and it's not going to be tomorrow either. So what is the challenge in getting us to fusion? And I know that I get the question because you would like me to give you a science answer or a technology answer. You want me to tell you exactly, like, if we fix this, then fusion will happen. So I'm not going to give you a science answer or a technology answer. I'm going to give you a different one. And this was inspired, I was really inspired by the Nobel Prize for Economics, because the Nobel Prize for Economics showcased that growth, sustained growth, requires active funding for fundamental science. It required somebody to pay that scholarship for Cecilia Payne to go and do her research. The second thing it requires, and this is a challenge, is when you actually create a new technology that is disruptive, it means an old technology needs to be replaced. And that is challenging. Just look at kind of how the energy spectrum looks like right now, yes? What are we typically fighting? There are people who have invested a lot of time, effort, and money into coal, natural gas, oil. They're not going to be too excited if a new disruptive technology comes around that will replace their technology and would remove their streams of income. There's a way to manage that. And so for me, one of the things is, so first, one of the things you need, people actually did do the calculations. How much do you need economic funding to actually achieve fusion? And so they did these calculations in 1976, kind of at the height of the oil crisis. And what you can see in black is the line of funding we have. So maybe the fusion never people are correct. But I don't think it is because we don't know how to do it or because we are not curious enough as humans to figure this out. It's not because I don't believe we're not tenacious enough. I mean, damn it, my mother thinks I'm stubborn. My husband too. The other part is, if you are going to build a disruptive technology, you need people to believe in you. And so one of the things I like to do a lot, and I'm very grateful that this exists, is that we actually get to communicate with all of you. I get to tell you about why fusion is great, why I believe in it, but I also get to tell you why I think fusion is difficult. And I like to have those conversations, and they're important to have. And one of the best things is I'm in a children's book. I am, and that was a lot of fun. And I helped her write her second one, which actually came out in August, so that was a lot of fun too. So when will fusion be ready? Well, this is Lev Artsimovich. He was the Russian who invented the tokamak. He was the one who invited the British to come to the lab, which was at that point high security. And this was his fusion vision. He says fusion will be ready when society needs it. It's not a question of curiosity. It's not a question of ingenuity. It's not a question of tenacity. It is a question of whether we all want this, and if we do, we will get to fusion. And I believe that because this is my team. This is my team here at William & Mary of absolutely amazing students, postdocs, and I have now a new colleague here, so I'm very happy about that. So I have another faculty member, and we are all working towards fusion. And they are not just doing this in the lab, but they're also going to DC. They're also interacting with you all. And actually, in order for you, since maybe I'll get 150 questions today because everybody wants to ask a question, but they are all wearing purple t-shirts. Yes? I will actually show you what these t-shirts look like. They're going to be wearing a purple t-shirt, just like this, and you can ask them anything about plasmas, fusion that you would like. They have exhibits outside. We also have Hampton University outside. They are a partner in our path to fusion, and they actually will have a little stellarator out there for you to look at of what that looks like, the stellarators today. The other thing I wanted to do is, because Peggy graciously sat through all this thing, I wanted to actually gift her this t-shirt, because this allows you to ask her questions now too to see if she paid attention. So I think with that, I have, only this last slide to leave you all with. Thank you. So I don't know, you want to do questions or something else?
I think that I speak for all of us when I say thank you so much. This was not only entertaining, but also gave us things to think about as we think ahead. And also for those of you who thought that you knew what William & Mary is today, well, I think that this is a nice window into what we're doing and how we're helping bring together everything that makes us strong and contributing to what society needs. So thank you, Saskia, and feel free to ask questions. I mean, my t-shirt is just a gift, and I'm not gonna be able to give you good answers, but there are many people who do. So, Saskia, I think you can really...
My face. Good. Hi.
Hi, Professor Mordijck. Thank you so much for this presentation. My name is Sean. I'm a William & Mary alum from 2024 and 2025. Actually, some of my buddies were your research assistants, Julius and Leo. And I had no idea they were doing cool research. I'm actually, I'm actually with the Virginia Department of Energy now. For
Nice.
the
Welcome.
Clean Energy Innovation Bank. So we fund research just like yours. But my question is, as a William & Mary alum, how is William & Mary positioning ourselves to help the Commonwealth Fusion Systems Project, which we funded? Because MIT is doing a lot of work. Is William & Mary involved at that scale?
At this point, so he's talking, so there is this company, I had a little slide up, Commonwealth Fusion Systems, and they're willing to build a power plant in Chesterfield, Virginia. And so right now, Bob and I actually graduated about the same time. So I've known Bob for a long time when he was still at MIT. We are not directly involved with their program at this point because they are just building stuff up. But they do use our research. So one of the things is we have very close relationships with MIT, and some of the things we are developing are actually critical needs for them to use down the line. So right now, I mean, if they are willing to pay us, then we'll take any money at this point, you know. Any source of income.
Thank you, that was fascinating. My question is, why do we need a temperature 10 times what the sun needs to sustain the same type of reaction?
Okay, because the sun is much more dense than what we do. Actually, the sun is much denser than Earth. So the funny thing is, when you look at the sun, the first thing you imagine is that you could just fly through it, yes? No, that surface is hard. And so actually, when you look at some of the laser work that is going on, they can actually create things that are closer to the sun in how dense it is. So what it just means is the reason we want to go to these high temperatures is because then we don't need to have as much fuel and we don't need to keep it contained as long. The other thing is the sun has been around for 5 billion years. It has a very good containment vessel, yes? Many more years compared to the kind of seconds, minutes, and hours we're talking about. Okay? Thank you.
More question before we enjoy some food outside?
Okay.
Do you think that humans as a society will actually ever be able to feel open to the idea of using plasma energy as a type of energy more accessible to people?
So actually, some of my friends do active research on this topic. So one of the things is you can do research on a lot of things. Yes, we can do physics research, but we can also kind of engage with other people and do kind of group studies and kind of look at interactions. And so the moment that you do something like this, but even in a smaller group, you kind of bring people together and you talk to them and you listen to them, most people find fusion actually an interesting idea to follow through. I think from my perspective, what is really, really important is that we're very honest in those conversations. Yes? Anytime there's a disruptive technology out there, people are scared. And that is normal. We are scared of what we don't understand. I mean, we've built whole myths and religions around things we sometimes don't understand. And we want to kind of be able to feel safe. And so it really requires us to be honest and to be open and to have a conversation. Does that answer your question? Good. Thank you. Okay.